So the goals for today are comparing two means. Now we're going to be looking at using the normal approximation and also we'll be looking at confidence intervals. As a quick review, remember we've been working with the explanatory variable when it's categorical and it has two categories, and the response variable is quantitative. We can compare the average response across the two groups. So that's pretty cool. When we look at it, we're actually able to compare them by looking at the average response between the two. We're going to use the randomization test for quantitative response applet to investigate, well, we have used it, to investigate whether the difference in means is unlikely to have happened by chance alone. All right, so is it just happening by chance, or is something special happening? Is our alternative, do we have any support for our alternative hypothesis? So then we, based on our p-value, we can conclude and talk about, and we have to include information about the research question and have a full conclusion. So in this example, we want to start with a study. Do men with children tend to live longer than those without? So for a statistics class project, some Cal Poly students randomly sampled men from the obituaries page on the San Luis Obispo Tribune's webpage between June and November of 2012. For each man selected, they noted the age at which the person died, the number of children under survived by. So complete numbers 1 through 6. Note, under subscript, for use none for no children and subscript had if they had children. That way you'll be consistent with what I've done. So pause, give it a shot, and come back. Okay, hopefully you're just going to be checking now the observational unit. You could say each man or each obituary. Either one is totally fine. It's like, well, how would I know? Well, they randomly selected men from the obituaries page. So we're looking at obituaries page, we're also looking at the men. Either way in this case would work fine. Usually we only talk about, there's one, but each of those would be fine on the exam. The explanatory variable, remember we're looking at whether or not they had children, which is categorical. If then what the response variable is what their lifespan in years was, that's quantitative. You could have also said, instead of lifespan in years, you could have said at the age at which they died in years, quantitative. Either one is fine. Don't get too hung up if your wordings aren't exactly what they are in the back of the book, as long as, or when I do this work, as long as it makes sense and what you say is pretty similar to what I've said in general. Is this observational study or randomized? It's an observational study. You can't, I mean, yes, they randomly chose, but could they choose who had children, who did not? No. Okay, so they didn't have any control over the response variable. The parameters of interest, mu had is the long run average lifespan for men who had children, and then mu none is the long run average lifespan for men who didn't have children. You notice we're talking long run average, all right? So we're looking over not just this, we're over this sample, we're trying to talk about what happens with men in general. Do they live longer if they've had children or not? The hypotheses, the null, once again, nothing special is happening at all, and the mu's are the same. Mu had equals mu none. Men who had children, men who didn't have children have the same lifespan, versus the alternate hypothesis where we're wondering if men who had children live longer. In other words, live longer here, we see had children. Men who had tend to live longer than men who didn't have children. So I used an applet here because I had the data, and you're going to have a lab where you'll have the data and can put it in. And I generated these bar graphs. Interesting, the ones men who had no children versus men who had. Just by looking at it quickly without looking at any of the numbers, let's not worry about the numbers yet. When I look at this, it's pretty evenly distributed for men who didn't have children. Excuse me, would you say that the average, just looking at that, is lower than the average for the men who had? I'd say yeah, because the average is probably right in here, whereas you've got this nice big group up here, so it's probably quite a bit higher. And let's see if that holds true. Summary statistics, remember those come out in the applet. None, and you can always double check your counts to make sure that everything looks okay. Out of the 90 that they sampled, 20 people had no children, and 20 men did not have children, and 70 men had children. The means are quite a bit different. 63.9 versus 78.43. You'll also notice under the men who did not have children, the standard deviation is quite a bit lower, quite a bit higher for men who had none. And that makes sense because this is very spread out. These red are really, the observations are very spread out. So does one group appear to have a log? So actually what I'd like you to take a minute and see, now that we've talked this through a little bit, is answers questions 7, 8, and 9. So hopefully you got the same answers I did. We already talked about the 7 men with children appear to live longer, higher variability. Looking back at that, men without, sorry, I've lost the zero, the O there. I should have an O. Men without children, because the standard deviation is larger. We see that here. We also saw it when we looked at the data, right? Because it's much more spread out. Now, by how much is the observed average lifespan of the had children group higher than that of the no children group? So this is when we're generating our statistic. X bar, remember that's the sample average had versus sample average none, and take those literally from the applet. A lot of times actually it shows you right here. You just see, be careful, make sure it says difference in means. But you notice I rounded to 14.53 just to make it a little bit easier to deal with. And on an exam, I would tell you how many digits I would like you to go to. So far, so good. Now, the key question is, remember, if men with children tend to live just as long as men without children on average, so saying nothing special is happening, how surprising would it be to see the difference of 14.53 years? And we can measure this, remember, using the p-value. So in the past, what we've done is simulation. So with a tactile simulation, take a minute and complete that part and see how you can do with it. So in general, if I saw something like this before we go any further, 14.53 years, that's a lot of years. It's probably meaningful, but is it statistically significant? So we need to keep going and actually come up with some information. Could it have happened by chance alone? By chance alone? Of course. But how unlikely is it to have happened by chance alone? So once again, we're going to look at the null distribution, but first of all, we're going to generate it. Now, this would take a lot of time. So if we're using cards, we would need, hopefully you came up with this 90 cards because there are 90 men or 90 obituaries. On each card, you're going to write the lifespan or the age of each man. Now, obviously, you would need that data. You would have to have it listed. And the way I generated on the previous page, that chart, I actually had the data spreadsheet, the Excel file with the data in it. Then we're going to shuffle and deal into 2 piles where 20 in one pile represents no children and 70 in the second pile represents they had children. Could you have done 70? You've put 70 here with had children and then 20 here with no children? Sure. The order in this case is not important. It's just more showing that you did do 2 piles and that it was 20 to represent no children and 70 had. Then after you shuffle them, you're going to record the difference, X bar had minus X bar none for the shuffled data. What do we do then? We repeat steps 3 and 4 many times to generate the null distribution. So hopefully this is feeling, I don't want to say second nature, but we've done this lots of times, all right? Because this is where that feeling of, okay, I understand, we're just generating what would happen if nothing special was happening. We're generating that null distribution. So then we calculate the proportion of times after we've done that at the end here, we calculate the proportion of times that X bar had minus X bar none is greater than or equal to 14.53 in the null distribution. So this way we can see how unusual 14.53 or more is to have happened just by chance alone. So as we said before, that is pretty time consuming. I just scrolled that, pause and scroll down a little bit. This is just on the next page. So instead of doing this by hand, fortunately what we can do is we can use an applet instead. Now, in this case, we're going to use the randomization test for quantitative response. This is from an Excel file or some sort of data file, a text file. I clicked clear, and then I copied and pasted my data in here. At the very, if you scrolled this all the way to the top, you would notice at the top it showed had and had, none, and then the count, all right, or the age, excuse me. And we have exploratory variables and the response variables we can choose there. The summary statistics, which I had shown you earlier, are right here. I did not have, right down here would be that difference in means, but I didn't copy that over here because we've already seen that. Now, what we want to do though is we want to take this in the same place, so this is on the same screen, we can generate that null distribution. So I'm going to shuffle, pretend there's 1,000 shuffles. This is just the results for the most recent shuffle. And then I'm going to say, okay, I'm going to look at this distribution. I want to count the samples that are greater than or equal to 14.53. And if you see that here, I wrote over it, it's 0.0, oops, 0. Let's try that again, 0.0030. That's a pretty small number, okay? And even if you look at it, you can see that it happens very few times. So interpret the p-value in the context of the study. I suggest pulling out your notes, taking a moment, and seeing if you can at least think through how would you word it. Okay, knowing that you've got a very small p-value. Okay, if men with children tend to have the same lifespan as men without children, we would observe the average lifespan of the 70 men with children would be greater than the average lifespan of men without children by 53 here, sorry about that, or more years about 0.3% of the time. So that's very, very unusual. Now, is that my conclusion? No, remember, this is just saying that we found something with the p-value. We found that it's very unusual. So next, we want to go and just to step back here, looking at number 10 again really quick. If you look, remember we state the null hypothesis here, so there's the null. Right? And then we talk about what we observed, what we would observe, talking about the sample, and our p-value down here. All right, so if you're going, and then this is all what we observed through here. So when you're looking at that, you know how we have the, I don't want to say boilerplate, but it pretty much is a boilerplate, like, okay, null, talk about the sample, talk about what we observed, and then the p-value. Now, do we pretty much have a boilerplate with the conclusion? Yeah, we really want to, based on our findings, we want to formulate a conclusion. We want to be sure to address SGC every time. Significance, are the results statistically significant? Causation, is it okay? Can we conclude cause and effect? And generalizability, whom can we generalize these results to? So my gut says this is very, very small. So this is just, listen to my gut here. It is statistically significant. It was an observational study, right? So no cause and effect here. That's my gut thinking about it. And who can we generalize it to? Well, it's a pretty small study overall. I would just say it would be more like men, just looking at it. And if you go back to the chart that we had on page 241, I believe in this text, you would see it would just be two like men in the study. So let's see if that works out. The small p-value, so I talk about that, provides very strong evidence that men with children do tend to live longer than men without children, but we cannot conclude that having children causes higher lifespans. Remember, we don't have cause and effect. We didn't have random assignment. All right, so cannot conclude cause and effect. These results can be generalized to men like those in the study who are similar in socioeconomic background, etc. So what we've done, this is what we've done many, many times so far. And hopefully, if you're not comfortable with it, go back through this again before you move on. So we found convincing evidence that men with children tend to live longer than men without children on average. What would the next logical question be? Well, I'd be curious. We have that 14.53, but that's just, is that the exact parameter value? Well, no, obviously not, because we don't know what the parameter is. It's unknown to us. That's that on average, how much longer do men live? Well, we don't know if they have children. So how much longer do they live? How would you answer this question? Well, there are different ways to answer it, but one way is that we can estimate the difference in averages. So we can estimate the difference in averages with, I wonder if any of you are thinking about this, I'm kind of leading up to it, with a confidence interval. All right. So when we're comparing, so before we go on to confidence intervals, when we're comparing two means, the normal approximation or the theory-based inference, the bell curve, can be used to determine a p-value like we have before, or it also can be used to develop a confidence interval for the difference of the means. So that's pretty cool. And you're like, well, why is this so important? Well, way back before we had computers and could do large simulations like we've been doing, we need to use the normal approximation quite a bit, because this way it gave us certain rules that we could use, and the math was, instead of having to flip cards thousands of times, we could use a normal approximation instead. So the normal approximation is only valid when, this is where it gets just, you have to be a little bit careful. Both sample sizes are large enough. Large enough being 10 to 20 times usually the size of the sample. So if I sampled 20 students at Cal Poly, do you think we have 10 to 20 times 20? So do you think we have at least 200 to 400 students at Cal Poly? Well, yeah, we have thousands and thousands, okay? Or the samples come from populations that are normally distributed. Honestly, you're usually not going to check that. You're not going to know that specifically. We don't want them to be largely skewed. So how do we check these? The validity conditions as a loose rule to check is both sample sizes are at least 20 or they come from populations that are normally distributed. How would you know that? You would need to be told that, or you'd have to have a graph of the sample data to see if it's reasonable to say that they come from populations that are normally distributed. In other words, the graph isn't really skewed. If it's super skewed, and you say, but at least 20, well, what do you think? If it is skewed, 20 is enough, but would more be better? Would a larger sample size be better? Definitely, okay? But for right now, we're more worried, is there at least 20 in each sample? Each sample being the men who had children and the men who did not have children. So it's not like if you had 10, say, well, I had 20. No, you have to have 20 in each. If the normal approximation is valid, we can use the theory-based inference applet, which is really powerful. So let's start with verifying that it's valid to use the normal approximation-based approach to find the p-value and the confidence interval. So let's look at none. This is definitely not skewed. Oops, sorry, not skewed. And n equals 20. So the sample size is small, but it is 20. It just meets that 20 minimum that we have to have. Data's not skewed, so I'm not worried at all. It is a relatively small sample, but like I said, 20 is our minimum, and it's not highly skewed. Had children, this is definitely skewed, right? It's skewed left because we have these few observations here that are going to pull the mean this way. But my sample size is quite a bit bigger. It's 70. So it is skewed, but the sample size is much bigger than 20, so I feel pretty good using the normal approximation. So n greater than 20 for both samples. So yes, the sample sizes are large enough. They're at least 20. They're at least 20. So we're going to use that theory-based applet. Remember, if the normal approximation-based approach is not valid, what should we do? What can we use? Simulation, all right? Simulation is always valid to use, unlike the normal approximation, all right? So you can always go back and use simulation. So I went to the theory-based inference applet and I opened it up. So here it is completed for you. The first thing I did is you have to change the scenario to two means because that's what we're looking at. Group one, we're comparing, group one to group two. All right, group one, I know is what we're looking at, the had children in this case. Because we're doing had minus none, you notice it reports the difference for us right here. So I might as well put them in the right order. At least for me, it makes sense. Had and none. So I plugged in the data that I had gotten from when I used that randomization applet. Now, in a lot of cases, you'll be given this data directly. You'll be told in a table, and you'll work on this on homework, where you're told the sample size, the mean, possibly the median, and the sample deviation. You should fill in the information it asks for, and obviously this does not ask for the median. So I put in 70, and then the 78.43, my mean, and my sample standard deviation, and I did that for both groups. And then I clicked calculate. So I had cleared all the data out and calculated. Now you see, I've got my mean and it tells you which group it's for. It doesn't do it by name, which is a little unfortunate, but that's okay. And you can see that the mean is quite a bit lower for group two than it is for group one. So where do I go now? Theory-based inference. So you're going to want to check here, test of significance. Remember, this is our hypothesis testing. So we want to look back at our hypothesis. Now here they do it by subtraction, okay, instead of equals. So this would be, let's just get rid of this for a second. This is hypothesis testing here. When we do test of significance, remember just two different ways of saying it. This is mu1 equals mu2, and this is mu1 is greater than mu2. All right, so be careful here. You have to make sure you have to change that, okay? Either less than, greater than, or not equal, depending on the situation. And then you hit calculate. In this case, my sample mean, the mean, excuse me, of my null distribution ended up being 0.00, which is pretty nice for calculations. Standard deviation is 6.021. And then I clicked, when I could calculate, up popped my standardized statistic. Don't worry about degrees of freedom in this class. T is 2.41, and my p-value is pretty small. It's 0.0122. My confidence interval, I checked that. You can fill in whatever value you want for your confidence interval. You don't have to use 95. You can use 97, 98, whatever it asks for. So we want to interpret the 95% confidence interval in the context of the study. So we have to be very careful when we do this. So that's why I wrote it down ahead of time. So what we can say is we are 95% confident that the long run average lifespan of men with children is greater than the long run average lifespan of men without children for men like those in the study, somewhere between 2.06 and 27 years. Now, we're talking difference here, right? So we're thinking it's going to be that men with children live anywhere between 2 and 27 years longer, all right? That's not saying what their lifespan is. It's saying that they're taking the men without children, and men with children tend to live 2 to 27 years longer. All right, so that's where you want to be careful. It's not a percent, 2% to 27%. It's not their lifespan. This is saying how much longer, because remember here, we're looking at difference of means, right? Whenever we do this. So it's, could we do 99%? Sure. There's lots of things we can do. Now, this is the only lecture this week, which probably seems a little bit crazy. There's going to be a lab or a worksheet for you to do for tomorrow. I've also posted the answers for that. Make sure you do it. It talks more about these, all right? Then you're going to learn more about confidence intervals and how they work. One thing I did want to point out before I ended this lecture, though, is you notice that the confidence interval is 2 to 27 years. What doesn't it contain? It doesn't contain 0, all right? So one thing to keep in mind is if my confidence interval contains 0, do you think it gives me, so that there's no difference between the two, does that give me does that provide any support that there is a difference between them? Does it provide support for the alternate hypothesis? The answer is no, all right? Another thing to keep in mind as we work these is if we looked at a different sample of obituaries, we wouldn't likely have 14.53 again as our difference, all right? But we are 95% confident that the average we would find would be somewhere in this confidence interval.